Good morning, class. This is Soumya, and I'm going to be talking about the second chapter of BIO 101, which is the chemical context of life. And we will be exploring details on how different elements exist, in what forms, and how much is required in the body, and what are the different kinds of bonds with which they are attached to each other, and so on. Okay. So, as usual, I always put a few important points that you should know about this chapter, and that is most of the time in my second slide as listed here. Okay, so we start with talking about matter, and as you can see, everything that exists is composed of matter. And if you break it down into its smallest form, you can call they are elements which belong to one particular category. So sometimes, say your own body is composed of matter, but it is composed of different things that are there. It has proteins, it has sugar, it has fat, it has so many other things. Now then, when you look and break down that to find out what that is composed of, so like for example fat, you can say it is composed of carbon, hydrogen, and oxygen. So there you go, you have your simplest elements being listed out. Okay, now, so an element will be just that material, and the most basic form that it has been broken down to. Okay, and a compound will be a combination of two or more elements. Okay, now, in human body or in any biological living system, and in this case we are talking about human body, and in that, if we are going to list out what are all the different elements that we are composed of, we can classify them in a certain way, and which is easy to remember. So the largest quantity, or the major elements, big percentage of them is present. And what are they? I would like you to remember something known as HONK, which stands for hydrogen, oxygen, nitrogen, and carbon. Okay, and this is composed of 96% of the living matter that exists in a human system. Minor elements. Okay, now I just want to remind you that all of them are essential. They are composed of three major parts. One is major, second is minor, the third is trace. All of these are essential. Okay, so the largest quantity that is present is of hydrogen, oxygen, nitrogen, and carbon. Then you move on to minor elements, which is present in lesser quantity, approximately comprising of 4% of the matter. So I have divided it into mnemonic, which will help you remember the entire list. It is composed of caps and clams. Now, what is caps? Ca is your calcium, phosphorus, and then you have potassium, and then you have sulfur, okay, And clams, you have chlorine, excuse me, then you have magnesium, and sodium. Okay, then you have a group of elements which are essential but are present in extremely small quantity. You can say 0.01% of the body material is composed of these elements. They are iron, copper, iodine, selenium, fluorine, and so on. Fluoride. Okay. Now, the one would think they are present in such small quantities and the body can do without them. It is okay, but that is not the truth. The reason is, if you are lacking in iodine in your diet, you can end up suffering from a disorder or a disfigurement called goiter. And this actually happens for people living far away from the seashore, because the sea and fishes are a major source of iodine. But there are people living in the mountainous regions who do not have any access to iodine in their diet, because the soil doesn't contain it, the water body doesn't contain it, so they just don't have this, in which case they would suffer from this particular disorder called goiter. Okay, then you have certain elements that are present which are toxic, which are harmful for us, and list of them is as follows: lead, mercury, arsenic, and so on. Okay, now here in this case, what is shown in front of you is what you have as a situation where initially at the base level sodium is a metal and chlorine is a gas, but they combine together to give you a salt. So this is like an emergent example for an emergent property. What I mean by that is, on its own, sodium is a metal, so it has properties which are totally different from what sodium chloride has. And on its own, chlorine is a gas and it has properties which are absolutely different from what sodium chloride has. So in their one step below, when they exist as is, they exist with different properties, different appearance, and so on and so forth. While when they combine together, their properties change and their appearance also changes. Okay, so this is like a list of all the essential elements that are present in human body. Okay, this is a woman who is suffering from iodine deficiency, and she has got what you call as goiter, wherein her thyroid glands have swollen up. Okay, here in this case is in a farm, if you have the soil which is deficient in nitrogen, okay, what happens is you would have stunted growth. Okay, the smallest form of any element is, which still retains the property of that element, is an atom. Okay, and an atom is divided into three parts, which I think most of you know: protons, which is positively charged, neutrons, which has no charge, and electrons, which are negatively charged. Now, protons and neutrons exist together. Protons and neutrons exist together in what you call as the nucleus of the atom. Okay, they are the ones which contribute to the weight of the atom or mass of the atom. The electrons, though they have a charge, they do not contribute to any significant mass. So, an analogy of how they exist in an atom, the way it is explained is, think about a football field, an entire big huge football field, and think about the eraser that is found at the back of a pencil. Okay, so your atom is as big as a football field, and the nucleus, which contains the proton and the neutrons, are contained inside this, and two flies flying over the football field contribute to the electrons. So this is like an analogy to help understand what is the size of each of the subatomic particles that exist and what kind of influence they are able to have on the atom and how much of free space exists in an atom. Okay. Then we are going to talk about something known as atomic number. Okay. Now, in order to understand an atomic number, you basically have to think of this as something in equivalent to your social security number. Now, what do I mean by that? Meaning you have a social security number and that identifies you and just you, nobody else. If the number changes, it is not you, it is someone else. Got that? So what I'm trying to say is there is something known as an atomic number, which is the same as the number of protons present in the atom of any element, present in atom of any element. Okay, and that is specific, special for that element. Okay, if that changes, then it is no longer that element. Okay, so you also have the next term that you have to know, which is called the atomic mass. Now, the nucleus of an atom contains the protons and the neutrons. Both of these together contribute to the mass of the atom. Okay, so atomic mass is the number of protons plus the number of neutrons totally comprising of the term and conforming to what is known as atomic mass of the atom, because the electrons do not contribute to any weight for that atom. Okay, and the way it is represented is, if I have an element, say an element X, okay, in most of the books, the way it is written is, in the top you have the atomic number. In the bottom you have the atomic weight. Sometimes it is the exact opposite in certain charts, in certain textbooks. I don't want you to get thrown off. What is more important is you would see on an approximation, whatever this number that you see, this number will be more. and that will give you a clue that that is the atomic weight. Okay, then we move on to another term called isotopes. Now, what do I mean by isotopes? Okay, so to understand this, first you must know that if you have carbon, okay, you can have C. Now, atomic number for carbon is 6. You can have C12 carbon, you can have C13 carbon, you can have C14 carbon, but it will always have atomic number as 6, which means this is what decides that this is carbon and nothing else. Okay, it is what is representative of carbon. Okay, so that exclusivity still exists, but if you notice, the atomic weight is different. Why is this atomic weight different? The atomic weight is different because the neutrons, number of neutrons, varies. In nature you find it. Naturally it is like this. So that does not mean this carbon is different from this carbon in any of its specific properties. It might have one extra property. It may have one extra property. Sometimes, like C14 is radioactive. Okay. Now C12 carbon is the one that exists in a maximum amount found in nature. Okay. There are C13 and C14 types of carbon. C14 has a special property. It is also radioactive. Now, an element which has the same number of protons but different neutrons and so different atomic weights is called an isotope. Okay. So, what is the requirement to mention this, and what is the use of knowing that an element is radioactive? Okay, because of that, there is a plenty of different experiments for which you can use this radioactive carbon. For example, you can radioactively label a certain drug, okay, and when you feed it to the person, you can find out what is the path that it takes, okay, and where it goes and deposits itself in the body by later on checking them through a scanner. And so you will know where the drug goes and takes effect and so on and so forth. That is one of the ways. Another way in genetic experiments is you can radioactively label DNA molecule and then check for its presence or absence or the kind of activity that it does and so on. In many genetic experiments you can use it. Okay. So here they have done a PET scan to find out, they have radioactively labeled iodine to find out where it goes and deposits itself, and that gives them an idea of different medical problems and to make conclusions out of it, make diagnosis out of it. Okay, so this is just to explain the structure of the atom. In this particular case, this is your nucleus, which is composed of the protons and the neutrons, and there is a cloud of charge, negative charge, which is exerted by the electrons that are present. Okay. Okay. Now, you have to understand the next step that you have to understand is behavior of electrons and so the chemical properties. Okay, for that, first thing that I can tell you is there are certain rules in which electrons, if they are present, how they exist around the nucleus of an atom. Okay, suppose this is the nucleus of the atom. Okay, and suppose there is just one electron, so it has a certain defined orbital around which it will revolve around the nucleus, and this is how it will exist. Supposing there are two electrons, they both will be sharing the same orbital, but they will never try to touch each other. They will be always far, but they will revolve around this particular orbital. Supposing there are three, then it would occupy the next orbital level. Now, why didn't it come here or here? Okay, studies have shown that there are specific numbers of electrons that can be present in different orbitals, and that is a given, that is like a mantra. Okay, so the rules in which the orbitals have electrons, the number of electrons that they contain, there is a certain rule. The first orbital, okay, can contain 2 electrons, up to 2. The second orbital can contain up to 8. The third orbital can contain up to 8. The fourth orbital, now one is most of your level of chemistry requirement or knowledge of chemistry that you need to know for this biology level, you only need to know up to this much. But there has been cases where students ask me, what is the number of electrons the fourth orbital can have? Okay, so then we found out up to 18 it can have. So in life, all atoms want to reach stability. Okay, so what they would do is they would at most try to have the number of electrons in their orbitals, like in the first orbital they would like to have 2 and be stable. In the second they would like to have 8 and be stable, and in the third they would like to have 8 and be stable, and so on and so forth. Now this particular rule or this particular situation is what makes them react with other elements, form bonds, take electrons, lose electrons, share electrons, and so on, and do whatever that it takes for them to achieve stability. Okay, now I would like for you to also understand what would happen if you heat an element. It would get heated up. How does it heat it up, and how does it react, and how do you know that it is heated up? What does it do? Okay, an example is, supposing this is your car and this is the bonnet of your car, and this is the wheel, and this is the wheel, okay, and this is the door, whatever. So this is the bonnet of your car, and you have the sun. Now this is made of metal. Okay, now what happens is sun's heat is falling on this. It's heating it up. Once it is heating it up, it is exciting the electrons. Okay, so the electrons absorb energy. Once they absorb energy, they get excited and they move out of their orbital. When they move out of their orbital, now anything that, like for example, there is this boy who's throwing a ball up. The ball goes up. Will it stay up? No. It has to come down. Right? And the force with which it's coming down, it will sort of bounce and go back. Kind of. This is the kind, and bounce and then find itself down here. Right? Similarly, if we are talking about the electrons present in the orbital of the metal element that is present on top of your car bonnet, it would get excited, absorb energy, and move out of the orbital. Okay, but all things that go up have to come down. That's law of gravity. So when they come down, what will they do with that excess energy that they absorbed? They give it off as heat. And that is why, and that sort of is like the heat that is radiating out. And then when you touch it, all that energy is transferred into your hands and you feel hot. Your hands and you feel hot. All right. So the same way you have to understand the energy levels that exist in the different orbitals is sort of given off stepwise, one below the other. Okay, kind of like ball falling down in a staircase. It doesn't fall directly down, it falls in slowly. Okay. Okay. It provides an analogy for the energy levels of the electrons that exist in the different orbitals. Okay. So this is your first shell which had the lowest energy level, the second shell which had the higher energy level, third shell which has the highest energy level. So if an electron moved from here to the next, it has absorbed a lot of energy and gone to this level, and it has to release it out to come back to this level, to position 1, ground 0. Okay, so the rules of distribution I already explained to you. Okay, now this sort of gives you an idea of one, what the electrons do in order to achieve stability, meaning in each of their orbitals. For example, I have hydrogen. It doesn't have a nucleus. Sorry, it doesn't have neutrons, no neutrons. It has one proton and one electron. That's it. This is your hydrogen for you. So what happens is the proton exists in the nucleus part of it, okay, and the electron is floating around. Now, how much do you need to be stable in the first orbital? 2. Now, that is why hydrogen will react with anything that can give it one electron for sharing. Please, it's very important for you to understand that it is only asking for a sharing purpose. So what happens is, in natural state, hydrogen does not exist as atomic hydrogen, just H. It exists as H2. Okay, so why does it do that? There is one hydrogen here, another hydrogen here. The two electrons that they have, part of the time this hydrogen shares it and uses it to gain stability. Part of the time this hydrogen shares it and uses it to gain stability. So valency of hydrogen is 1, meaning it needs just 1 to complete its orbital. Okay, now different elements that exist have different valencies depending on the number of unpaired electrons that are there and how much they need to complete their outermost shell and become stable. Okay, so here you have hydrogen. Remember, hydrogen is the only one which does not have no neutrons. Okay, it does not have neutrons. Everyone else will have neutrons. So if you notice, helium out here is atomic number 2 and atomic mass 4. which is a combination of the number of protons and the number of neutrons. Now if you notice, it has got atomic number of 2. That means its orbital is satisfied. It is stable. In other words, it is inert. In other words, it does not react, not reactive. So helium, neon, argon, radon, all of these are in the end of the column where they have stable outermost orbital and so they are called noble gases. Okay. Whereas you notice like carbon, in the first orbital it has 2, in the second orbital it has 4, so it has requirement of 4 more in order for it to be stable. Nitrogen on the other hand has 2 in the first orbital and 5 in the second, which needs 1, 2 and 3 more in order for it to get stable. Oxygen on the other hand, okay, it has 2 in the, it has an atomic number of 8. It has 2 in the first orbital and 3, 4, 5, 6, 7, 8. So that means 6 in the second orbital. It needs 2 more in order for it to be stable. Okay. Fluorine on the other hand just needs 1 more in order for it to be stable, and that's why it's extremely reactive. Okay. And different elements have different valencies. You should be able to draw the valency knowing the orbital electron filling rules. Remember, the first orbital 2, second orbital 8, third orbital 8. So you should know how to draw this, and in order for you to find out what is the valency of each element that is asked. Okay. Okay, so here I have put a list wherein the major elements that we are going to be dealing with through and through as part of biology, which is part of biochemistry. We need to understand the these elements, their valencies, and what is their atomic number, and so how they would how much they would be reactive. Okay, so hydrogen requires, it has an atomic number of 1, it has 1 electron, maximum 2 is allowed, and its valency is 1. Oxygen on the other hand is 8 and its valency is 2. Nitrogen, the valency is 3. Carbon, the valency is 4. Carbon is called tetravalent. Okay, so here we can see that hydrogen, oxygen, they do not have a choice that they can stay in their elemental form. So they are more stable if they exist in twos, in pairs. So they can do something known as sharing of electrons in order to maintain stability. And we'll talk a little about water in a while when I'm talking about the different bonds that are possible. And methane here again is carbon, as I told you, is tetravalent, meaning it had 4 electrons in the outermost orbital. It needed 4 more, so it is very versatile. It is capable of bonding with anything and everything that can give it electrons. So that is the reason you have carbon forming different kinds of bonds, and you have something known as hydrocarbons existing, and little more about them in a while. Okay, so when electrons are shared, meaning part of the time one atom keeps it and part of the time the other atom keeps it. This is the contract. that is called as covalent bonds. They are the strongest bonds. Okay. In that covalent bonds, you can divide it into two parts. You can call it non-polar covalent bonds and polar covalent bonds. What do I mean by polar? Opposites. Two different things, meaning two different things and two different ends. Okay, so that means at the end of bonding, one side and the other side, when you compare, if there is no special difference in a charge, they become non-polar. They don't exhibit any special charges, they are non-polar. Okay, so an example is one hydrogen bonding with another hydrogen. Okay, this is going to be a non-polar covalent bond wherein electrons are equally shared and life goes on. On the other hand, you have something known as polar covalent bonds. Now, there are two examples with which you can understand this particular kind of bond. Let's take the example of oxygen. First and foremost, oxygen is electronegative. Meaning capable of attracting electrons. Okay, so oxygen had an atomic number of 6. So in the first, this is my oxygen, this is the nucleus, first 2 electrons, that leaves us with 4. I'm sorry, oxygen has atomic number of 8. I apologize. So in the first orbital, it takes 2 electrons. In the second one, 3, 4, 5, 6, 7, 8. So it leaves us with a space where 2 electrons are required in order for this to become stable. What does it do? Okay, it has a contract with hydrogen. Hydrogen has 1 electron. It needs 1 electron. So one hydrogen bonds with the oxygen and they have a contract with the oxygen to share electrons for part of the time in the orbital of hydrogen, for part of the time in the orbital of oxygen, and with the other hydrogen atom on the other side requiring this. What does the outcome of this kind of situation? So everything would have been normal and we wouldn't be even talking about it, and life would not exist if oxygen had behaved himself. But oxygen went rogue. He went against the contract. What did he do? He backed out on the contract. So here you have the oxygen and it has 1 hydrogen here, 1 hydrogen here. He just keeps the electrons to himself and does not part with it. Why? Because his nature is electronegative, and that is the reason it is difficult for hydrogen to pull back its electrons. And so what is the outcome of this kind of sharing? It is still sharing, okay? This kind of cheating sharing, this side of the water molecule where hydrogen is present is slightly positively charged. Why? Because only the proton is present and you can see and feel and experience the charge of the proton on that side. On this side too, you would have just the protons exerting their charge and you can feel it. And on this side, because of 2 extra electrons, oxygen is slightly negatively charged. So you can see polarity kind of like how you would see in a battery. Yeah, kind of like that. One side of it is positive, another side of it is negative. Okay, and that is what is polar covalent bond. This kind of situation also exists with nitrogen. Nitrogen is got a valency of 3 and he is also electronegative. And so when nitrogen combines with ammonia, refuses to part with the electron that they took from hydrogen, and this side is slightly negatively charged, this side is slightly positively charged. So that is the story of polar compounds and polar covalent bonds made by the combination of oxygen and hydrogen or nitrogen and hydrogen. Okay, so this is what is depicted in the picture to show how you can have a non-polar, no fighting, dull, boring kind of bonds wherein you have no charge at the end of this particular relationship. Whereas water molecule, you end up having a polar covalent bond. Okay, now we move on to the next set of bonding, which is called ionic bonding. Now what is this? Ionic bonding is basically completely sorry, bad spelling, completely donating or accepting electrons. We can take the best example of sodium and chloride. Sodium has an atomic number of 11. Chlorine has an atomic number of 17. So let's draw their charges and see what happens to their orbitals. So first orbital for sodium, 2 electrons, gone. Second orbital, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so that's your 8 electrons for you. And the third electron, the 11th electron is present. Okay, on the other hand, chlorine, okay, 17, right, atomic number. So 1, 2 in the first orbital, second, 3, 4, 5, 6, 7, 8, 9, 10. And the third orbital, 11, 12, 13, 14, 15, 16, 17. That leaves with one space. Now, is it easier for sodium to try and find 7 more electrons or to give away 1 electron? It is easier to do this. On the same note, chlorine. Is it easier for chlorine to find 1 electron or to try to give away 7 electrons? It is easier for it to find 1. So this relationship is sort of like the best relationship ever. Sodium gives this electron away, donates it, and chlorine accepts it. What is the outcome of that? Sodium has got now a stable orbital, okay, of the last orbital that it has, which has got stable number of electrons, which is 8 electrons. But what is the result of this kind of donation? It has more positive charges than the number of electrons. So This sodium now is positively charged. It's no longer an atom. It is not an atom. It is an ion because it is a charged atom. On the other hand, chlorine, because it accepted this extra electron, what is the outcome? It became stable, but the net charge that chlorine has is negative because it has one extra electron in it than protons, which makes it positively charged. Kind of like this picture which depicts the whole thing that I drew in the previous one. Okay, now most of the compounds formed by ionic bonds are ionic compounds. They are in salt form. They are very strong as long as they are dry. Like sodium chloride exists as stable salt. It is often found in nature as crystals. It's very strong as long as it is in solid dry form. The minute you introduce water into this story, it changes the scenario. What happens is all those bonds between the two, the ionic bonds between the two, is just lost. So sodium ion goes one way, chlorine ion goes the other way. Both of them go their ways. Okay. Then you have something known as hydrogen bonds. Okay. What is this hydrogen bond? Now, hydrogen bond basically is a very transient bond. It is there but not there. Let's find out what this mysterious kind of explanation means. Okay, so let's take the example of water. Okay, now water molecule has got 2 hydrogens, 1 oxygen. And what is the way in which it is present? Okay, oxygen, hydrogen, hydrogen. So this side is slightly negatively charged, this side is slightly positively charged. So another water molecule which comes into action here, what would it do? Because of these charges, the oxygen would be like this. Right? And then another one would probably be attracted slightly towards the hydrogen of the other molecule. So there is a slight transient bond. So this bond that exists is the hydrogen bond. Please be mindful. A lot of time when I ask what is a hydrogen bond, bond between 2 hydrogen, bond between oxygen and hydrogen. That's what my students say. And that is not accurate. Why? You have to explain that it is bond between hydrogen of one water molecule and oxygen of another neighboring water molecule or any other compound. So this kind of bonding is a hydrogen bond. You make it and you break it. You make it and you break it. As many hydrogen bonds that exist is what is capable of keeping water a liquid and giving it a lot of different properties, which we will be talking about in the next chapter. And let's move on. What else is present in this? Okay, so this is how you can see the transient hydrogen bond that exists. Oxygen of one water molecule and hydrogen of another water molecule. All right. Ammonia also is capable of exerting hydrogen bonds because of the polar nature of the covalent bond that it forms with the hydrogens present in it. Okay, then you come to a certain kind of bond which is a very weak bond, but in large numbers it is effective. So every compound, polar, non-polar, have positive and negative regions. This is all the time changing. Okay, that is only possible when molecules and atoms are very, very close. So imagine you take a Ziploc bag, okay, and everything is here. So then when you move the Ziploc bag, everything moves this way. When you move the Ziploc bag again, do you see what I'm saying? So it sort of falls. So kind of like that, everything that exists is sort of shuffled towards one side. So in the one side of the molecules will start to exhibit a certain charge. Okay, and this is exploited by the foot pads of a gecko, which has cells, hair-like cells, in the projections, which have the opposite charge, and so they are attracted to this end. The best way I can explain is how a gecko can stay stuck on the ceiling. Yeah, and that is because of this weak bond called van der Waals forces. So there you have your gecko who has a lot of hair-like projections, and these cells have a lot of charges in their outermost edges, which get attracted to the wall and helps it stay stuck. Okay. Now, we talked about different kinds of bonds. We are done with the kinds of bonds. Now, in biology, you also have to consider the shape of a molecule and how it exerts an important effect on the functions. So, one example is I generally, if I am in the class, I ask my students that you stub your toe against the table and then you scream a little, you swear a little, you hold on to it, and then you just sort of press your foot. You wait for that pain to die off. You're literally pressing that foot. What basically you're doing is you are forcing your cells to secrete endorphin. Endorphin is a painkiller. So, because of the pain, you feel the pain, the information goes into your brain, and then you hold on to your stub, you scream a little, you swear a little, and you breathe a little, and then you would end up, what do you call? You would end up secreting endorphins. Okay, so morphine that exists is a plant product. Okay, now why does morphine also give me an analgesic feel? Why is it like a painkiller? It is not made by humans. Okay, why is it recognized by humans? Okay, to understand that, you have to look at the structure of endorphin and morphine. Okay, so this is your natural endorphin. So it has this structure which is recognized by the receptors, meaning certain parts of the cell which recognize the shape, because it is like a good fit. So this is your natural endorphin and this is the receptor for it, and it recognizes. Morphine, on the other hand, has got a structure which resembles the structure of the natural endorphin, and so it is recognized by the endorphin receptors, and so it exerts the same painkiller property. Okay. Now you have chemical reactions which exist, which basically involves making and breaking of bonds, which changes the composition of what you started with and you end up getting something else. So you cannot make something out of magic. You can only make something out of what exists by changing the bonds, moving around, changing the proportions of whatever, and then you end up getting the products. So whatever you start with is called a reactant. What you end up with is called a product. The whole process wherein reactants are converted to products is called a reaction. It is very important to balance, to make sure what you started with, of all the things, should be accounted for. The reactions can go forward or in reverse depending on the the status in which it exists, depending on what level to what level it is moving, whether it is spontaneous, whether it is energetically favorable. Okay, so here you have two hydrogens. Okay, so this is one hydrogen, this is another hydrogen, okay, which is reacting with two oxygen, with an oxygen molecule, okay, and the bond here and here is broken, the bond here and here is broken, and fresh bonds between this guy and this guy is made, so giving you the product. But if you notice, it has to be balanced. What do I mean by that? If I have two hydrogens of hydrogen molecule, which is 4, I should have 4 here. If I had 2 here, I should have 2 here. So it has to fit. It does not mean it is equal in concentration. It is just that the concentrations have stabilized in that ratio, and it is a dynamic kind of stabilization. Okay, sometimes you have a forward and a reversible kind of reaction written. The reaction is going on, but there is no effect in the change or concentration of the reactants and the products.